I'm sure I don't need that stuff. I don't have time to walk across school ball field. I don't either. Sometimes you need to. Oh. Very good. I think I can go home and not a cake. This time of Joe just sent me down 100 more pages. So helpful.
I think there was 1 or 2 missed ones.
And we're going to start. Garrettsville has set up a water monitoring program, and it was came about as a result of a lot of drilling leases being sold in the area, and a lot of other communities having difficulties with water issues. And being a Board of Public Affairs person, your ears perk up when you start hearing water problems. So rather than wait around until we have an issue at our water wells themselves, we decided to set up a monitoring program. So if there was going to be an issue, we would know about it ahead of time and have time to figure out what to do about it. So we had a lot of people involved in setting up the water monitoring program. EPA was consulted, ODNR, Portage County Health Department, Jeff Sheehan, our water superintendent. So it was not just brainstorm of any one person. This was a compilation of a lot of people putting their heads together to figure out what to do. We ended up hiring Dr. Jeffrey Dick and Anna Draa from JD Environmental Consulting. They are the people with the geology knowledge, and they will explain to you more about what the program's all about and the analysis of the results, because now we have data to analyze. So, without further ado.
Thank you, Fran. Yeah, I consider it to be a real privilege for Anna and I to be selected to undertake this project. One thing you have to realize about this project, it really is at the kind of forefront of this sort of activity in Ohio, at least from the standpoint of municipal water supplies like the village of Garrettsville, actually taking a proactive approach to protect the water resources that they have. And as time goes on, I think this sort of studies kind of become more and more common. Oil and gas is not anything new to eastern Ohio, but what is new about the shale gas that's coming, or is here in a lot of places well established, like here outside Garrettsville over towards Windham, is that the scale of the activity is much larger than anything that we've experienced before. The volumes of water that are used in the hydraulic fracturing process are much larger than anything we've seen before. And because of the horizontal nature of the drilling, the fact that they're hydraulically fracturing shale, it requires a significant amount of chemical additives so that the hydraulic fracturing process will actually work properly. And because of that, there's a lot of legitimate environmental concerns. Contamination at the well site, over-extraction of water. What do you do with this water and the brine that comes out of the wells? In Ohio, it's disposed of in Class 2 injection wells, of which Portage County has about the most. It might be tied with Stark County, I'm not sure. But a good number of injection wells in Portage County. And you might ask why, and I don't want to deviate too much, why Portage County has so many. And the primary reason is that Portage County sits on the northern edge of the Ravenna-Clinton oil field. And you'll see in a slide here the good amount of Clinton oil wells in the area, as well as deeper Rose Run wells. And in order to service the brine that was produced from those wells, Portage County got a significant number of injection wells. And that's primarily why they're here. They're not here because Pennsylvania brings stuff in or West Virginia brings stuff in. It's true they do, but the majority of the injection wells in Ohio were here long before drilling of the Marcellus took place, and they were here to service Ohio's oil industry. So what we're going to present here today, or this evening, is kind of an overview of what we've done. I'm going to cover the geology and some of the basic stuff, and then I'll let Anna step up and cover some more of the interpretation of the results that we got. Before we get started, special thanks, and Fran mentioned a number of these people. Of course, Fran and the Board of Public Affairs, Keith with Portage County Health Department has been a great help. Keith right here, and then Jeff with the Superintendent of the Water Department, Dwayne Porter, on down the list. A lot of people have helped out in this. Just to get you started, we're basically up in this area, of course, but this map, I'm not going to spend much time on it, shows the distribution of oil and gas in Ohio. The early discovery of the Lima Finley oil field out in western Ohio. This gave rise to Standard Oil of America. It was at the time, in the late 1800s, the biggest oil field in the world. The oil that was produced from this field, and also extends into Indiana, but the oil that was produced from this field was derived from the Utica Point Pleasant Formation as the source rock. Moving over to the eastern part of the state, after this played out, a lot of oil and gas was already being produced out of eastern Ohio. This is in fact where oil was first discovered, but over time it became clear that eastern Ohio was where the majority of the production would be held. The colors you see in red and pink represent natural gas. The colors you see in shades of green represent oil. And in this area over here, the Clinton Formation has been the most prolific producer of oil and gas in eastern Ohio, and it covers a pretty good region. There's other formations like the Berea Sandstone, for example, which here in area Garrettsville is a borderline aquifer. It's a little bit saline, but once you get over into Mahoning County and further south, like down Columbiana County where I live, it's an oil-producing formation. Here's what Garrettsville area looks like against the backdrop of traditional oil and gas drilling. It's a fairly high density of wells. The majority of these, probably 90% of them, are Clinton Formation wells. The Clinton Formation is about 4,000 feet down. It's about 2,500 feet above the Utica. And it's been a prolific producer in Ohio.
When did most of those get drilled?
Most of these were drilled in the 70s and the 80s. And it was spurred on by stimulus from the government, high natural gas prices, a variety of different things, tax incentives. But this is pretty much drilled at capacity right in this area here. So it's been a fairly prolific producing area. And it shouldn't be a surprise that with all of these existing traditional oil and gas wells, there might be some contamination-related events. Well, we know about the traditional oil and gas. Let's move to the non-traditional or unconventional. Unconventional is what we call drilling for shale gas. It's unconventional for two reasons. It involves a horizontal leg of the drilling. Directional drilling is something that the oil industry's been able to do since the 1940s. So that's nothing new. It also involves hydraulic fracturing. Something else the oil industry's been doing since the late 1940s. And really took off in the 1950s. And so what hydraulic fracturing does, and here's a traditional vertical well, is it increases the permeability or the ease with which oil and gas will flow to a well by creating artificial fractures. And it's done using water pressure. That's why it's called hydraulic fracturing. Prior to hydraulic fracturing, they had nitro-shot stimulation, which was basically setting off nitroglycerin explosives in the well. Sometimes it would make for a great well, other times it would destroy the well. And it's also very dangerous. And so hydraulic fracturing was a big boost to the oil and gas industry. It's been a big boost to Ohio. All of these Clinton wells, Rose Run wells, they've all been hydraulically fractured. So we take this traditional vertical well that's been hydraulically fractured, and now what we're going to do is we're going to drill down the same formation, but instead of just fracturing, let's say, 500 feet, now you can fracture much more by drilling horizontally, and each one of these sets of fractures will be a stage similar to one of these. And it doesn't take a whole lot of imagination to realize that when you can bore through this much of the formation, fracture this many intervals, you're going to get much greater, potentially much greater production. And that's what's driving shale gas. Basically what it comes down to in the United States of America and pretty much North America, we've depleted the easy, inexpensive to get to oil and gas from traditional formations. And what we're seeing in Ohio, this is about the 5th major oil and gas play from shale that can be found in the United States. And this isn't something that's going away. It's going to continue to grow. It's present throughout North America. Eastern Europe is looking into it. South America is looking into it. China's looking into it. It's rapidly expanding. It's here in North America because the technology was developed here, particularly by Devon Oil with the Barnett Shale out in Texas. Some of the things that are important to realize in this type of drilling is that it differs from traditional vertical wells, in which usually there's 3 strings of casing. Conductor stabilizes the well, surface casing protects the groundwater, and then production casing, 3 strings. These horizontal or non-traditional shale gas wells typically have 5 different strings of casing. And so they're more robust construction to them, but that doesn't mean accidents can't happen. It doesn't mean there can be some construction problems. And so one of the things that's been identified in traditional oil and gas wells as a problem is integrity of the cement that bonds the casing to the borehole, or sometimes the actual casing itself corroding away. That's associated with traditional oil and gas. There's no reason why it shouldn't be associated with non-traditional. A little bit more robust construction, probably less likely, but still it can happen. Now, we're about a month out of date here, but this is a map that shows where the Utica and Point Pleasant, they're 2 formations. Actually, it's not the Utica that's being drilled, it's the Point Pleasant. But the Utica is so much easier to say, that's the name that's caught on. The Point Pleasant's right underneath the Utica. All the drillers, when they came in, the early drillers were looking at the Utica, but they quickly realized, go a little deeper to Point Pleasant, and that's where the pay zones are. And so this map shows, using different symbols, where the activity is. And Carroll County is still where the heart of the activity is, with Chesapeake. But as you move further into the south, Belmont County, Guernsey County down this way, start to see a lot more activity because they found some very rich productive zones down here. But in all, there's 23 operators, 20 different counties that have permits, not all drilled, but permits. About 693 permits. This changes every day. Currently, about 29 wells drilling. All told, 329 wells as of the beginning of June had already been drilled, and it's now about, I think, 108 wells that are actually producing. And so this is moving along. But one thing you have to realize, this is very early in the whole process. This is year 2. We're just completing year 2. And if you compare this to the Marcellus in Pennsylvania, it's moving along at a similar rate. It's anticipated that the latter part of this year, in 2014, is when you're going to really see things picking up in speed dramatically. And instead of 329 wells in 2 years, we might be looking at 600 to 800 wells per year. The reason for that is the midstream infrastructure that allows these wells to be hooked up, the natural gas separated from the natural gas liquids, the cryogenic processing plants. There's 4 under construction in Ohio. One's basically completion, the other one's very close. All right, so this is where the activity is. And of course, here we are up here. We're a little bit up on the northern end of things, but Portage County was a target early on by Chesapeake and now by Mount Air Keystone. Just to give you an idea of the graphic, you might hear from time to time that the Utica is a bust and they're all pulling out and it's not really what is expected to be. Those are all various interpretations of information, and we're not here to talk about that. But I've been keeping this plot going since the very beginning. First I was doing it every couple of months, and now I do it monthly. I actually do it weekly. And you can see that the amount of drilling is not letting up. This is a cumulative plot, and so it's just continuing to go up and up and up. This is a map that perhaps some of you have seen. You can get this from the Department of Natural Resources, the Geology Division, Geologic Survey. And what it basically shows, using the data that they have, which incidentally, I love the ODNR, I got a lot of good friends that work there. It's not the best data, and that's not their fault. They get well cuttings to work with. They don't get the well cores, they get cuttings. And so all these blue dots represent cuttings, but based on those cuttings, they've determined that the pink zone in here would be dry gas methane. The yellow zone in through here would be natural gas liquids, and then the green zone getting out here would be oil. As you get further and further to the west, the formation gets shallower and shallower until you get out here into about Wayne County, Medina County, Holmes County. This is where Devon came in very early and drilled some wells and had very, very poor results. They've packed up and left. They're not interested in this area. They still got leases elsewhere. But basically they found oil but didn't have the pressure to produce it. So this is the Sawinski pad, which I'm sure you're all somewhat familiar with, or maybe you've been out there. This picture's a little dated because there's now the 215 permit out there. We're looking at this area right here. Here's Garrettsville. We got the Brookover permit, which hasn't been drilled, and there's some talk about it being moved. And then there's the two Sawinski wells, the Mountaineer Keystone, are operating down here. And this Mountaineer Keystone's also bought this permit up here, or at least the acreage. Class 2 injection wells play into this whole study. We're fortunate in that we don't have any Class 2 injection wells within the actual water, natural water drainage, groundwater or surface water, but not too far to the north, right across the divide, we get into a couple of them right up here. But if you look at the distribution of Class 2 injection wells, they're all in eastern Ohio, and that's because historically that's where the production's been in Ohio. It turns out to be very convenient to Pennsylvania, West Virginia, to be able to truck their brine over for disposal, and certainly a number of new wells that have gone in close to the border are there to take advantage of that. So when we talk about production from any formation, but in this case the Utica Point Pleasant, you got to talk a little bit about the fluids that are coming out of the ground, because there's a concept that it's natural gas, it's oil, some of this wet gas we've heard about. Sure, that's what they're after because that's where they make the money. But another product that naturally comes with oil and gas is brine. A very high concentration salt water that dates back to the time when the sediments that make up the rock were being deposited in the sea. And then over time that saltiness has just gone up higher and higher. To give you an idea of comparison, if you've been to the Outer Banks, anywhere on the East Coast and got a mouthful of salt water, or you're playing in the surf, that's about 45 milligrams per liter. We're talking 100,000 milligrams per liter to be brine. So quite a bit saltier. The other fluid that comes out is flowback. And flowback is what comes out after you hydraulically fracture. So you pump 5 million gallons or so of water with a good amount of sand that props open the fractures and chemicals which allow the process to work better. You pump that in, and within the first couple of days of flow testing, you'll get back about 20% of that. At least that's what we're getting from the Marcellus, where there's a lot of published information. Utica, not enough information out there yet, but what I'm hearing is it's about the same. 20% comes back out, and you got to deal with that somehow as well. So, excuse the fine size font here, but this title of this slide is Potential Environmental Concerns, and we haven't even listed all of them. There's a number of them. But spillage of those production fluids we talked about. Accidents happen. Sometimes it's negligence, sometimes it's equipment failure. But those are realities of the oil and gas business. And that's really where the heart of the problem lies. It's not with hydraulic fracturing fluids coming up through fractures from deep in the earth up to the surface, like you might have seen in the movie Gasland. That's not where the problem is. The problem is with how do you handle these fluids once they're at the surface, and then some of the other things. So you can spill the hydraulic fracturing fluid. That's happened. Methane gas. Methane's common in our environment, but oil and gas drilling can do different things to increase the amount of that. Sometimes it's temporarily. In other situations, it can be for longer periods of time. Mud pits, which don't really use with the Utica, but these can leak. These are more traditional oil and gas. We talked about the casing and the cement that holds the casing in. You got to store these fluids when they come up. You have adequate storage space. Pipelines are starting to be networked all over Ohio. Pipeline accidents happen, bursts, all sorts of things, corrosion. Accidents while you're transporting produced water from the well to an injection well. Injection well operations, spillage, well design issues. And then there's always the possible exposure to radionuclides, NORM, which is naturally occurring radioactive materials, or T-norms, which are technically enhanced naturally occurring radioactive materials. The definitions of these really come down to government agencies and how they distinguish them and the regulations that go with them. Ohio generally goes with NORM. Your biggest NORM or T-norm problems are going to be associated with brine water that comes out of the well. So here's just a couple of pictures. Here's two brine tankers. This one's just dumping out on the ground. Here's an actual drilling fluids and mud pit, which you won't see with Utica drilling. Here's a water hauling truck that went off the road, but it could have been hauling other stuff. And then here's an actual frac job with the wellhead. And you can see the spider web of all the different tubing and whatnot, and just imagine the flanges that can break there. So the project that we're presenting here went basically in 3 different steps. The very first step was to go out and figure out what the existing groundwater situation looked like. And we do that by going out and looking at existing water wells, looking at the ones that are part of the monitoring program, and putting together groundwater flow maps, spatial analysis we call it. And that enables us to determine which wells we want to use. And as you know, we're using primarily domestic water wells owned by individuals in the areas surrounding the village, and also using the village water well. You can do a lot with geology, just looking at topographic maps. I love topographic maps, and first thing you can do is you can pick out where the bedrock is shallow versus where it's very deep. You got glacial fill. Garrettsville sits right on top of an old glacial filled valley, has a branch that runs up this way, and Eagle Creek has pretty much claimed that valley for its own. It didn't carve the valley, but it's the low area across which it flows. And so it helps define the geology. This goes back to something I did in the 1980s. I did a groundwater study for Lake County, and the geology is not that much different, but basically what we're looking at for water-producing formations, groundwater-producing formations in this area, would be the Sharpsville sandstone, which is part of the Cuyahoga group. This is the most prominent aquifer. The Berea sandstone, which is not all that great here, it's fairly deep. You gotta go down 250, 300 feet to get to it. The deeper you go, generally the more dissolved solids are. It's a little bit salty. And then over here would be glacial deposits that filled in the valley. And that would be right through here. And so these bedrock areas are pretty much Sharpsville sandstone and then glacial valley fill. Garrettsville gets its drinking water from a water well field up here in Brocious. Here's the town, and this is the general area that we looked at for the study. A little bit of information here. The water department established in 1907, and 90 million gallons of water produced each year, and that comes primarily, Jeff, out of 2 wells, if I'm correct.
That's correct.
Yeah, so you're very fortunate to have 2 very highly productive wells. When we look at natural groundwater flow, this is based on looking at water well levels, the levels of the water in water wells, and then taking into account the geology. We have the Grand River Basin, the Cuyahoga River Basin, Mahoning River Basin. And right up here on the very edge, these pink dots represent Class 2 injection wells. And so this is on a actual surface water divide. And so they're sitting right up here on the divide. And I want to let you know that these red dotted lines are drawn in very general fashion. They're not precise, but these are pretty much right on the border. You got a couple more here outside over the Cuyahoga River Basin. The Ohio Department of Natural Resources, Division of Soil and Water, and the Ohio EPA, they do a number of studies as a service to Ohio. And they do what's called a drastic map, and it's really a groundwater pollution potential map. And what they've identified in here is what we just pointed out. The blue areas are the bedrock highs, and then this is the glacial valley with an arm going up to the north. What we found with our
investigation basically goes along with what the drastic map was saying, but we've got a lot more detailed information with ours, not just general information. Division of Water, Soil and Water at the Ohio Department of Natural Resources provides a groundwater well locator, GIS-based map. And so here inside of our study area, you can see each of the blue dots represents wells that they have in their database. They keep about 40 to 60% in their database. When you pull up one of these water well logs, it looks like this. A lot of different information about how the well is constructed, pumped, tested, what it drove through. That's one of the things we're looking for. And then we're looking for information on the water production rates. After we put together a map based on the water levels we could get from public information, Anna here went out to the 19 different wells that we had established by cooperation with people like yourselves, and she went out and did static water level measurements so that we could put together a much more accurate map than you get from the stuff that's on the reports from Division of Water. And the map that we produced looks something like this, where the dark areas are high. This is a groundwater map, not a surface map. And these are 50-foot contours on here. And what the map shows is that water flows from the dark areas to the light areas. Here's that glacial filled valley that Eagle Creek flows through. Here's the water well field. And by simply drawing flow lines, which cross more or less perpendicular to the separation of these different elevations. This is 1100, this is 1050, this is 1000, this is 950, 900. The water is basically flowing like this and like this. And we concentrate on this area. The colored dots represent the wells that were selected for use in the study. And it's pretty obvious why we selected these wells, because here's Garrettsville's public well field, and here's the flow going towards it. And so we want to get water that is moving towards the well field and then pick it up and intercept it at these different monitoring locations to get an idea of the quality.
Can I ask you?
Yeah.
Can you give me, looking at that, like street names, so I have an idea?
Okay, this,
How far it is? Just an idea in my head.
all right,
That's 82.
thank you. This is 82 right here. Okay, this is what we came,
What's
Where?
82?
That diagonal curving north.
this one. And this is
That's Center Road.
Center Road, okay. And then Hiram's right over here, so we kind of,
You see the Nelson Circle up to the upper right there?
right
That's the
there.
Nelson Circle, so that's on Route 305.
That's 305.
88 runs straight up and down, north and south.
Yep.
So we're
Okay,
looking
thank
at all the way from Hiram to Nelson Circle, all the way down.
Yeah, we mapped that far out, but then we concentrated on this area here.
Yeah.
And the importance here is to be able to, and I'll let Anna talk to this more, but the importance here is to be able to monitor the quality of water such that if there is a contamination event, you have prior knowledge of it before the water gets to the production field. Also, if you have prior knowledge of your water quality, and through the program that Garrettsville's doing, you have a couple of years of data. If there is a contamination event, you've got a strong background, and that's why I call it a baseline study, of what the water quality was like prior to drilling activity. Now, the Sawinski wells over here won't have an effect on Garrettsville, but definitely this well up here, if it's drilled, the Brookover well, could have an impact because it's immediately upstream.
You made a distinction between surface water and groundwater.
Yeah.
What's the difference?
They're tied together. The groundwater in Ohio is replenished by surface water recharging under high areas, soaking into the ground, flat areas, sandy soil, whatnot, and then it enters into the ground, flows through the ground, and then naturally discharges into streams like Eagle Creek.
So groundwater is deeper than surface water.
Yeah, it generally mimics the surface topography, so if you've got a hill, the surface elevation's high, the groundwater elevation's gonna be a little higher, these are hills.
The bedrock can change a little different than a stream, it's all gravity.
And the surface water flows rather quickly, so you might measure that in feet per second after a heavy rain, but groundwater you would measure more like centimeters per second. It moves much slower. And groundwater is naturally cleansed to some extent by the subsurface materials that flows through.
So to go back to that map.
Yeah.
So the bulk of the recharge to the aquifer that we work off of here comes off of north of town there. So that's the recharge.
For the area that we're looking at, yeah.
That's the
This
recharge
would be a recharge
area.
area up in here, and it's influenced not only by where the high areas are, but by what kind of soils are at the surface. So if you got clay soils, it's not gonna allow much water to pass through it. If you got sandy soils in a relatively flat area, a lot of water will move into it. Sandy on a slope, not so much. So there's things that influence it.
So as far as our water goes, it's more critical for, in our way of thinking, to keep things not to the north of us, spilling wise, drilling wise,
There's a
injection well wise.
general practice in hydrogeology groundwater, it's called basically recharge protection zones. So you identify areas where water is recharging and you protect those. Along the Rocky Mountain Range runs a classic example where the aquifers of the western states are replenished, and so that's protected. Okay. All right, one more question, I'm going to let Anna take the floor.
This
Yes?
goes back a little earlier, but why doesn't Pennsylvania have more injection wells for all their oil and gas production?
It's part political and it's part geological. The geology side of it is that 2/3 of the state, the eastern 2/3 of the state, are not suitable because of the folded Appalachian Mountains, all folded and faulted. So it's pretty much the eastern third or western third of the state. The other problem that Pennsylvania faces is that they never applied for what's called primacy from the federal EPA. Ohio has control of Class 2 injection, as do 21 other states, but Pennsylvania doesn't. And so the permitting process, because you're going through the federal government, the red tape, you're looking at 5 to 8 years to permit a well, whereas in states that have control of it, they can do it in a much more efficient fashion. Also, the other political thing is individual counties in Pennsylvania, they don't set the regulations on how the wells are constructed, but they thumbs up or thumbs down on whether they'll allow them. And so it's quite a bit different in Pennsylvania than Ohio. Okay. Anna. Oh, the well colors. The pink wells in here are, we labeled them GL, that's glacial. That means sands and gravels of glacial origin, generally the best aquifers. BR is for Berea sandstone. There's only one of them on the map right here. It's a fairly deep well. Yellow is CYG, that's the Cuyahoga group. That would be the Sharpsville sandstone layer. So you can see that the majority of the wells that are being used are in the Sharpsville. And that's because the water has to recharge through that in order to get down to this area. And then there's a couple in here, there are combinations right here, that are glacial and Cuyahoga group. And so they have some sand and gravel on top of the Sharpsville sandstone, and they draw water from above. All right.
So as our three major task items for this study, we just went over groundwater flow, where water's coming from recharge areas and how it's going through the community. The next step was then to come up with sampling. And we identified the wells that we're going to sample and came up with a summer 2012 and a fall 2012 sampling and testing analysis. So I'll run through some of the results of that and then finish up with our conclusions and findings. So like Jeff was saying, the key to a successful study like this is establishing a baseline. Because drilling is starting to build up in the area, we want to create a background information database of what the water quality is now, so that if changes occur, we can identify those changes. So EPA, ODNR, Health Department all came up with a 3-tiered set of testing parameters. This was the template that we used. Tier 1, you can see the list of analytes. Tier 2 would include those analytes plus some additional parameters. And then Tier 3, this is where we get into the methane and the VTEX, which are the organics. Of course, cost is going to increase if you can conduct more analyses. Now, with that list of parameters, not all of them have health implications or negative health implications. So the ones that do have what are called primary standards would be barium, and then benzene, toluene, and the xylenes. That means there's a health standard established by the EPA. So if you were to exceed concentration of that factor, there would be problems to your health. A secondary standard, you can see here for chloride, sulfate, total dissolved solids, iron, manganese. These standards are set for more of a, it's called aesthetic. So if there's an odor or a taste or a color, it's not necessarily going to impact your health. It's just more for looks. You can see that a lot of these parameters don't have standards. That made our job a little difficult. So if you don't have a standard that you could say it exceeds, how can you rate it? How could you actually say if it's good or bad, or what does it actually mean? One important thing to point out is methane. We're going to see in the results that are presented that there were some wells with elevated levels of methane. And the key is that there's not a health concern as far as drinking dissolved methane in the water, but there's an explosive hazard. So if your wells are not vented, that gas can build up and become a hazard. This is a busy table. So again, this is the list of our 3-tiered set of parameters. The ones in red correspond to those with primary maximum contaminant levels. So you do have an impact to health over 2,000 micrograms per liter for barium. Again, I'm going to include methane in this because we do have some impacts, like I said before, with venting. If you have excessive methane, then the benzene, ethylbenzene, and toluene as well. Highlighted are the secondary standards. And then for these ones that don't have exceedances, primary or second, what we wanted to do was look at data that's been collected in the area in the past. And luckily the EPA has what's called an ambient groundwater quality monitoring program. And in that program, they have sampled groundwater throughout many Ohio wells. The years I had data for were from 1991 to 2007, and it was for our production well, well number 20. So I can establish levels for those parameters from that data as a comparison. Then I also wanted to list all of the samples that were collected went off to Alloy Labs, and the lab can only identify a parameter based on its equipment and how low of a concentration it can read. So I just wanted to reference those numbers there. So now we have a set of numbers that we can actually use for comparison. And again, it's not health related if there's not a primary or secondary. It's just sort of a starting point. Another great reference that we could have was from the study done in 2002, EPA. They identified what are called inner and outer protective zones. So this is around the well field. This is 1 year and 5 year. And this represents a travel time. So like Jeff was saying, groundwater does not move as quickly as surface water. So it would take roughly 5 years for water to reach the well field from this outer zone. So in the slides I'm about to show you, we incorporated the groundwater surface elevation map to show you flow direction, the inner and outer protection zones to show you sort of a time period reference, and then the data. In the summer, we sampled all of the wells within the area that we selected for the volunteer program. And then going into the fall sampling period, we wanted to evaluate and see, is it completely necessary to test all 21 wells again? Basically from a financial standpoint. So we came up with a ranking system. So the first set of data that I'll show you from the summer, you'll see data points for 21 wells. And then for the fall, we isolated and removed 4 of the volunteer wells from the study, and those are going to show you then the remainder after the fall sampling. And this is a good ranking system that we can reference in future monitoring. Again, finances are going to dictate how much data can be collected. So we can revisit which are the most critical, which are identified sort of in the blue, somewhat critical in pink, and then whether or not we can afford to sample the remainder. Okay, so this plot can get a bit confusing. It's just to show the distribution of that same ranking. So our number 1 well is going to be our production well, and then 2, 3, you can see the distribution. 4. This was a combination of, we took into account the results of the summer water quality. We took into account physical position based on the groundwater flow that we identified with our gradient. And we also took into account a bunch of other factors related to geology to come up with that ranking 1 through 21. First parameter I want to talk about, because we tested the 3-tier, I can't go through each analyte. That would take us all night and be very boring. So I've identified about 5 of the most, I wouldn't say critical, but target analytes that can tell the story of what's happening with the groundwater system. Because our goal is just to understand sort of the fingerprint of what the groundwater quality is now. So what we're looking at are the results of the water sampling, and we're looking at summer, TDS, total dissolved solids. The larger symbols here are over 500, and 500 is the established secondary MCL. And so you can see where some of these elevated TDS levels I'm getting hits for. If I go to the next, total dissolved solids, I'm sorry. Yeah, everything. When you say something, water is salty, it's a combination of minerals that have been dissolved in that water. It's sort of the layman's term to say it's salty. But TDS is a great indicator for overall water quality, because the more material that's dissolved in that water, the higher your TDS level will be. We go to the next sampling event in the fall. I'll kind of go back between the two. You can see for the most part, we don't have a huge change. We still have sort of elevated TDS concentrations in these pockets. Again, we're really only looking at the ones that are over 500. This plot, you're going to see repeated a few times. Along the y-axis is your total dissolved solids concentration. That red line is the secondary maximum contaminant level. Again, secondary meaning aesthetic. So it's not a health concern, but the higher TDS, you can have a poorer taste. So you see these dots here in blue represent the summer sampling, and then the green fall. Overall, the trend is pretty similar between the two seasons. We have one outlier that's too high of a TDS to plot on the map. You're also going to see this gray bar show up on a few of these images. Before I mentioned the ambient water quality monitoring program, these were the ranges for well 20, the production well, for what TDS was seen to be between 1991 and 2007. So it's just for comparison of what groundwater TDS is for this area at that production well. The next analyte would be chloride. Again, this is summer. And here we're looking at anything over 5. And again, there's no health effect associated with the chloride. We're looking at it just for comparison. We want to see trends and changes. The larger symbols, obviously, we have the higher levels of chlorides.
What's the secondary limit for chloride?
250 grams. Again, if I go back and forth between summer and fall, again, you can see we're dealing with a little bit of elevated concentrations in those same spots that we saw with elevated TDS. I didn't mention it before, I'm sorry. These other symbols that are sort of filling in the area, those are all of our conventional oil and gas, traditional wells. We look at chloride against the same plot. Again, our red line is the secondary, 250 MCl or milligrams per liter. For the most part, we have chlorides for both seasons below that level. Again, we have one well with exceedances above. The next was bromide. Again, we're looking at just changes. Bromide does not have a primary or secondary standard. But again, if we do see changes in the concentrations through time, it can indicate an overall change in water quality.
I have a question over here.
Yes.
If there is no established standard, read that, nothing that says it's bad, how did you pick that to look at?
Certain things, I'll show you another slide in a minute, are indicators for source of water.
Okay.
If I use chloride and bromide together, I'm going to show you it's a chart that'll tell you where we think groundwater is being impacted. And so this is why we use chloride and bromide. No health standards alone, but they're a good indicator as the fingerprint of where that water came from and what's been impacted in it. Yeah.
We also look at chloride and bromide because two common sources of chloride and bromide is brine water that would be produced along with oil and gas. And so they can both be elevated in chlorides and bromides, but chloride can also come from other sources. Road salt, near surface, salt layers, which we have in Ohio, things like that. So we look at them both to help distinguish the origin.
And I'll show you in a minute, we identified certain areas which wells were grouped and what type of environment that source water was from.
Thank you.
So the bromide, again, there's no red line because there is no health standard established by the EPA. And also there's no shaded area because the ambient program by the EPA did not test for bromide. So here's the chart that you're referring to. Each of these dots represents one of the wells. And this is during the summer sampling event. So if you were to take chloride and bromide versus just chloride concentrations and plot those values on this map. This chart was created by a study done in 2006 to look at source waters and what could be affecting the source of the chloride and bromide. So that previous study sort of gave me these trends. There are linear trends that once you connect them, create these polygons. So red wells with these ratios plotting along that red zone, we would say were affected by road salt. The orange animal waste, septic in purple, basin brines along the green, and this is important to point out. These basin brines, I don't want you to initially say it came from, you can't say that the basin brines came from drilling activities. It could also just be natural basin brine in the groundwater. Like Jeff was saying before, the deeper you go, in certain formations, you can have naturally occurring salt water.
Okay, can you give me a time frame of, when we're talking road salt, say it's December, say we've had a frozen December, all the way from December 1st to December 31st. They may have salted the road all month, every single day. Can you give me a time frame of actually when that salt could make it to my well? Can it make it there December 31st? Or can it make it there after everything's frozen, spring came and gone, and now it's May?
That's a great question. The study study where this originated from was to answer that question directly, and they were looking at neighborhoods that were urban environments with more cement, asphalt applications, so did the salt actually get in? And it all comes down to the geology, the height of the water table, and how quickly infiltration is occurring on your property. Do your soils have a lot of clays? Do those waters sort of build up and pond at the surface, or do they infiltrate rapidly? So it's different in every sort of, I don't know. Also, do you have a berm that runs along the road right by your property that can collect water and allow it to slowly infiltrate, concentrate?
Because it raises the next question, what if my well is 500 feet from the road versus right, one car length from the road, like, so there really isn't, so there's a.
Well, I could speak for this data.
Right.
And the wells that were impacted and plotted along this road salt linear trend were the ones along Grotius Road. Those are the only wells indicated from the road salt signature.
So that's telling us that the road salt affected that, is what that's saying?
Possibly.
Possibly.
Yep. This is the same chart, now including the fall data. And so, these graphs are hard to take by themselves, but if you have all of the maps laid out in front of you with the well IDs, you can start to see trends and where these certain areas are affected. And one that I remember is the Grotius Road, where these three right along here.
What kind of ratios might you have if we were impacted by oil and gas?
You would see an increase
In the green side.
Yes. And when we get to the conclusions, these 3 and 4 basin burn affected wells were also correlated with elevated TPS methane, all of the indicators. 2 more of these sets of data to get through. Barium. Here, again, notice the trend very similar to the other analytes we looked at in the summer and in the fall, not much of a shift there. Barium we're looking at, again, there's no health implication, but barium is used really highly in drilling for petroleum.
And back in that slide there, it showed barium production
Yes.
way up in the fall.
And way up is a relative term because we don't have a standard set for what we could call high, but yeah, an increase occurred between summer and fall. So this is one of the parameters we definitely want to keep watching in the next year to see if it's seasonal or if it's exponential and what's going to happen.
Would the levels change because in the fall, we had a pretty dry summer last year, so would we have had a higher concentration in the aquifer?
Definitely. When you don't have as much rain, your water table goes down and you're
Right.
essentially concentrating what minerals are in that water.
Right.
If you have a lot of rain during the season, your water table will rise, you have more of this volume of water, concentrations will go down. And that's what's so important about testing more than once. And especially doing it seasonally to capture those highs and those lows to give you the full range.
And that's specifically why we sample in the spring and in the fall to get that high point in the spring and the low point in the fall. It's common accepted practice.
Again, there's no health standard, but the ambient program did test well 20 for barium, and in the past, from the early 90s to the early 2000s, this was the range that barium was seen. So we have seen barium present, and the range, you can see here, that looks like it could be 60, 70, 80. Last one we'll look at is dissolved methane. There's no health standard, but there are recommendations for levels of methane. If you have present over 10 milligrams per liter, it's recommended that you have your well vented so that that methane doesn't build up and become a hazard. Here are the areas where we've seen elevated levels of methane in the summer. and then again in the fall. There's a lot of different factors that could go into why methane is fluctuating. It could be natural. I think more data will help answer a lot of those questions. So this is then showing us our methane plot with 10 being our standard, so to speak. And you can see the number of wells with exceedances in methane are greater in the summer than in the fall. But then again, notice that we only make it up to about 22 milligrams per liter.
Before you go on, could you go back to the last map?
Yes.
The red dot on the left-hand side.
This type?
No,
Oh, up here?
left-hand.
Oh, I'm sorry.
Right there.
This guy?
Yeah, that one right there.
Yes, sir.
That's on Wheeler Road.
Yes.
Okay, it's very interesting about where that dot is. Years ago, there used to be a dairy up there, and all of Garrettsville had their milk from that point, and all those maps showed
There's an elevation
a
there.
little higher concentration at that point. The dairy well was 125 foot deep, just down the hill, it's surface water practically, so.
Well, that's a good thing to mention, because this well is our deepest. It's the Berea well, over 300 feet deep.
Oh, that's, yeah.
So I think it's due to the depth of that specific well, where we're getting more
It went down until we could get with the water right across the street
Yes.
was a dump well.
Well, it's, the water level across that street is shockingly different.
Yeah, well, sure, it's surface water practically.
Right.
Well, there's a capped oil and gas well up there behind the old dairy too.
Is it
That's an old cap well.
this
so-
the one here?
Yeah,
Yeah.
yeah, there's an old cap well, so the Lord only knows what's going on.
And there's one hiding here, and I want to point that out because this cluster of monitoring wells is also seeing elevated levels almost every day.
There is a cap well around that.
Yeah. Yeah, the symbol's there, it's just hidden from the other. Okay. Oh,
The blue triangles, the wells, those are conventional
Yes.
drilled wells. Those are not hydraulically fracked wells.
well, the Clinton,
They were
4,000.
hydraulically fractured, but they're fractured basically using water, sand, and sometimes some hydrochloric acid, which sounds terrible, but it's really benign. So they don't use the chemicals.
or the volume of water.
Or the
Yeah.
bottles.
And then we said that the summer was, the methane was lower,
Higher.
was higher in the summer.
Correct. Oh, I'm sorry.
When you find this methane that has no health implication, is there a way to tell how long it's been there? No?
Without data, no.
Okay,
Yeah,
thank you.
Unfortunately, I wish there was.
Isn't there a way to tell whether you're getting naturally occurring methane from just rotting matter, so to speak, or from methane that's being generated deeper down from the oil and gas industry? Isn't there a test that?
You have to do
Isotopically,
isotope
yeah.
analysis, but you're talking biogenic methane by bacterial breakdown
Right.
versus thermogenic by heat process.
Right.
And you can do isotopic analysis, it's not that easy to do, fairly pricey, but you can
Yeah,
distinguish them.
but you can't distinguish.
Yeah,
between-
potentially distinguish them.
Okay, so to sum up, I just want to go through our conclusions and recommendations for the future. So overall, groundwater is moving throughout the area from the northwest towards the southeast. And these are approximations 5 to 20 feet per day. Again, much slower moving than the surface water would be. And the general trend and direction is critical to understand when you're looking at implications of drilling in areas surrounding your water source. Of the 18 inorganic parameters that were tested with the 3-tiered, thankfully there were no results that exceeded a primary maximum contaminant level. So it's a great thing to know about your water source, is that you don't have any of these health standard exceedances. There are, however, 5 secondary standards that were exceeded in some wells during certain sampling events in the summer in fall. And that was aluminum, iron, manganese, chloride, and TDS. Again, secondary is just aesthetic. The findings from the chloride bromide ratio comparisons gave results that one well could possibly be impacted from septic effluent. 5 look like they're impacted from basin brine. 12 from agricultural runoff, and 3 from the road salt applications.
So again, the basin brines could be natural or it could be from a improperly capped well.
Or it could be from, since these Clinton wells were drilled 70s, early 80s, standards for drilling were much different then. A lot of those surface pits were used to hold or store water, use water, and it's possible some of contamination that we're seeing today were the result of those poor or different standards for drilling back then. It could also be casing related. Even if those wells were abandoned, how long ago were they abandoned? Were they properly abandoned? What was the condition of that casing? How well was the job done? So,
Historically, most common problem with brine contamination from oil and gas drilling is leaking mud drilling fluid pits or improperly reclaimed drilling fluid pits. That's one of the big problems.
I would stop it.
well, that's no longer used.
Yeah, in the Utica Point Pleasant drilling, they use a closed system of steel containing structures. It doesn't ever touch the ground.
Which is good, but unfortunately, contamination that occurred decades ago can still be impacting current groundwater.
And these old wells wouldn't have been deep enough to be concerned about radioactivity?
The big concern about radioactivity is that organic rich formations like the Utica and Point Pleasant have an elevated level of radioactivity, gamma, alpha, beta emissions, and that's because uranium, thorium, and radioactive gas. It's not like you touch the stuff and it's hot and it's going to hurt you, but by drilling through those formations, there's different ways in which the radioactive materials can become concentrated, at least in greater concentrations than they occur naturally.
These are like considering that the same.
Right.
Sorry for all the text. Fourth conclusion was about bromide. In itself, it's not considered very dangerous, but during treatment of drinking water, with bromide present, you can create THMs. And the best way to prevent these trihalomethanes from being created during the water treatment process is to eliminate bromide from that source water to begin with. It's just a lot more cost effective and proactive.
Can you
Barium.
explain what that THMs are?
I'm not that familiar with it. Jeff, I don't know. During the disinfection process, during treated water with bromide present, THMs,
Yeah, the trihalomethanes are formed with that.
during that,
Yes,
if bromide is there, disinfectant, they combine.
with chlorine, yes.
So if we can eliminate bromide from even being introduced during treatment, we don't have to worry about this being, and the level is 80 micrograms per liter, where you can start to have health impacts in drinking water.
So the village would have to treat more if that were to elevate to too high.
It becomes more complicated, costly. Barium, even though we don't have a primary MCL for barium, again, it's a good indicator for water that has been involved in the drilling petroleum process. So it's a good analyte to look at for changes, especially if we see spikes as we collect more information. Of the 8 organic compounds that were also tested during the 3-tier analysis, again, luckily there were no exceedances for primary MCLs. However, we did see elevated levels of methane in these wells. And we also subsequently found sort of a trend. These same elevated levels of methane correlated to elevated levels of TDS And the chloride bromide ratios also indicated influence from the basin brine. Putting all of that together, elevated methane, high TDS, high basin brine influence, one conclusion we could make is that the inactive Clinton sandstone well with this number that's located right next to those monitoring wells could possibly be the reason for those elevated levels. It was drilled back in 1979 and went down approximately 4,300 feet.
You know when they were capped?
I'm unsure. The information I could find was very little. An intensive site-specific investigation would have to be done to look into how that well was constructed, what records were kept on it, possibly a site visit.
ODNR doesn't show it's being plugged and abandoned.
It just says it's inactive.
They can stretch that out for a while.
So they have an orphan program that they could come in and do something.
It's probably doesn't even qualify as an orphan well. It's the operator of the well is not producing it and has some exemptions.
I got you.
It's stretched out the process, which is, there's a number of avenues to do that.
Are those 4 well numbers there, are those all along Mills Road?
No. They are sorry. Here are these 3, and then this one here.
So
The
three
Berea-
of them are on Mills Road?
Correct.
And it's unquestioned, but Mills Road is about a quarter of a mile long. Why did you select 3 wells in a quarter mile stretch to monitor
It
of the
was
whole area?
based on the groundwater gradient flow. These are the areas where we have those flow vectors drawn for where recharge is then going to divert water towards the well field.
Not everybody was willing to
Yeah,
let
that was a
us
big
use the
thing.
well.
Okay.
So, that's a
Thankfully-
major,
It just seemed like,
yeah.
I know that street is,
Yeah.
that long, and I just was curious.
And again, that's another reason why we did the well ranking, to try to eliminate duplication of efforts. If we have a well right next to another one, do we really need to sample those again? Good question.
Can you move that one screen up? The last one. Yep.
Do you know who drilled that well?
I may have brought papers, I don't know. I do have the name actually right
The
now.
vertical wells we're talking about, that's what you
That
mean. Oil and gas. No, gas well.
I did put it in there.
Okay, I can sort of talk about recommendations. That's the last 2 slides. Basically, it was, okay, great. We found out we don't have any primary exceedances, so our health, the overall health of our groundwater is very good. Secondary, we have a few. Now, those 5 that did have secondary exceedances are very common for groundwater in Ohio, so it wasn't shocking to see some of those elevated levels, especially iron, fairly common. But what do we do now? We have to make recommendations for the future. Again, we're at the forefront of this process, even though the EPA, ODNR, have come up with these 3-tiered analyses, we don't really have a standard to follow as far as what to do. So what we think is best for the community and keep an eye on the water quality is to then test the next year seasonally. So to do the round in 2013 in the spring, which was already done, and then to do another one in the fall. And with that data, we can add to this database and see what trends we can follow. I'm done. Okay. Thank you. Sure. Again, with methane, if you are concerned about elevated levels of methane, the best thing you can do is install a vented well cap on your well. It still preserves the integrity of the well, but allows the gas to escape. And again, this is just to go through, what do you do? Okay, so far we haven't had any primary MCL exceedances, but let's say in the next sampling period we do see one. What you would have to do is then resample, make make sure there wasn't negligence involved or an error in the lab. If it comes down to where we see an issue, the next step would be a full site investigation. From there, we could actually identify the source and come up with a timeline and an actual set of steps to take to preserve the water downstream. And that would involve contacting Ohio EPA and ODNR. Again, future monitoring, thank you to the BPA. We are on contract now to analyze the next round of data. So through 2013, we can come back and discuss the updates this coming year. We're already started. And then in the future, if for cost savings purposes, you want to reduce the cost for all of this work, one option is to go back to that ranking system and sort of cut back the number of wells that are being tested, but keep the same standard in place for the future. Tons of references. There's a sign-up sheet in the back. If anyone's interested in additional information, my cards are there. Feel free to email me, or if you want to put your name on that list, give me your email address or mailing address, and I can provide you with more information.
Just to remind everybody that as the levy passed, the health department was able to reduce the rate for the sampling by $50, so it's almost 100% less. I think we're getting $10 for bringing me out there. So let your friends know. It's on our website if you need an application. Pretty simple process.
Okay, thank you very much. And if you need to contact either myself or Jeff, please feel free.
Good job.
In your research of our aquifer system here, I think we're kind of in a unique situation with the headwaters of Eagle Creek, Silver Creek, Camp Creek, and from what I saw on the map there, the replenishing field is north of town. Was there any way that you have any kind of an idea how much volume of water is in our aquifer? I guess my concern is when the oil and gas industry does come, and they will come, and they're using 5 million gallons for every leg off of a well, which could be a dozen legs. That's a lot of water, and our streams are not, we don't have the Mississippi running through here, so they're going to be after water, and I was concerned that they'd be drilling high output water wells, and is our aquifer system going to be large enough to sustain that, or are we going to have to drop our wells down into the Berea sandstone to get water again? Do we have that situation?
One of the problems with Ohio geology or hydrogeology is that it's unusual to drill a well that can produce those kinds of volumes of water out of the ground. They do exist, but they're few and far between. And so their primary source for water is going to be, it's going to remain surface water. And because of the Great Lakes Compact, they can't go to the north. They got to go to the Mahoning drainage basin. They can't use the Cuyahoga or the Green River.
Well, maybe they can't pull that much water out of one well, but they can certainly build water wells for people drill compared to oil and gas. And you just said Garrettsville, they pull what, 90 million gallons a year out of one or two wells. So
It's not much of a wise, you can't call it widespread practice at all. It's very isolated where they use groundwater.
I don't have the slide to show this, but Jeff was gracious. He gave me data for wells 19 to 20. So speaking of that volume of water being pulled out, actual drawdown of how the water table adjusts was fairly, I can't remember the numbers. Drawdown from production.
61 to 88
50?
feet.
what, 50 inches?
What'd you say?
Feet.
Feet.
Yes,
50 feet?
typically.
Sustained, and then if you would shut off pumping, it would recover relatively quickly.
I'm more worried if they go into the smallest drain. They don't have to get a permit unless it's over 100,000. so they can come in and do that and really harm the street. If they stay with
One
the
person in the-
Mahoning Rivers and in the West Branch, is, I don't think it's gonna impact water at all. As long as we keep them out of the street. That's my personal opinion. I just don't think we're gonna see it.
And Garrettsville's water well, is it, where is it? Is it down in the Berea?
No, it's in the glacial
It's
valley.
in the glacial.
Yeah,
Valley
that's
fill,
why
which
it's
is
so
That's why it feels so.
pretty high yielding sand and gravel.
That's where the Lifting Streets well as well, there also.
Very much so.
I agree with you.
Yeah, that's a sand gravel road. Yeah, they mine it.
So, there's not being any issue with them pulling water out of the rock.
You're not gonna have the village that's selling enough water to hurt them.
Well,
So
the
you've got that
village,
factor.
the village only goes out a little ways. I'm not talking about buying a hotel, I'm talking about
Great amount.
drilling. I've seen some wells out in the west that they hear that's well.